Okay. Hi, everybody. In this lecture, I am going to show you how we can generate a sine wave in LabVIEW with a noise or with added noise, and how we can filter this generated wave and carry out some related measurements. I shall use a high-level virtual instrument in LabVIEW called simulate signal, which is used to generate sine wave or another standard waveforms like the triangular wave, for example, or sawtooth wave or square waves. In order to make use of simulate signal VI, you need to go to the main palette as you see here. Then you go to express VI's palette. Here is the palette of express VI's. And at the input palette here, you select simulate signal. You press it by the left side of the mouse, and you will have this page opened. You can select the signal type you want to generate. Either it is a sine or square wave, triangular, sawtooth, and even DC level. I am going to generate a sine, so I keep it on the sine. Here you have options to select, like the amplitude of the here it is given 1. For example, if you want 2, I can write 2. When I press OK, now it is now with 2. The level here is 2. The maximum 2 and the minimum is 2. If you want to determine the number of samples, here it is as a default automatic and given 100 samples. But you can uncheck it here and add here a different number, for example 50, and then you will have now a signal with 50 samples, not with 100 samples. If you want again with 100, you will have the previous shape as it was before. If you want to have 1000, it will be, of course, with a more fine. This is 1000 samples. Preferably keep it to automatic, and if you need to change it, you can change it whenever you want. You can also generate the sine wave by adding a noise. You tick here, and now you will have a noise added, and you can also manage the level of the noise. The noise amplitude here is 0.66. Here now I can do it less, 0.2, for example. Now it becomes smoother, and it may be higher, 0.8, for example. Okay, now it is higher, and so on. So now we know how to generate, how to find the express VI and how to open it and to configure this palette in order to generate a sine wave. The generated sine wave will have a terminal here, and you can take it and work with it as you want. Again, if you want to check again what is there generated, or to newly define the parameters, you just click it here twice, and it will open again, and you can carry out the necessary changes. For example, the frequency here is given 110 hertz. I can increase the frequency to, let me say, 50. It is better as the network frequency. For example, now it is a frequency of 50, as you see, hertz. So it depends what you want. Again, if you are done, you can click OK, and now you will have the output. So now I have this output from here. This is as a cluster of values. I have added to this sine wave a noise externally. I did not add the noise internally. So I need to go to a palette where it is possible to generate a noise and to add the noise you want on the block diagram. To do that, you right-click on the block diagram and then go to signal processing. Here you see signal generation. Also, you have waveform generation. In either of them, you can find noise, how to generate noise, either a white noise or a Gaussian noise, it depends, or another kind. I am clicking on the signal generating here. You can see this is the Gaussian white noise. I press it and put it here. Now it is there. And I can work with it and add it here to the output sine wave. I am adding here really a waveform one, and I'll show you the difference just now. So I right-click here, go to the signal processing, waveform generation. Here also I have this VI, which is called, as you see, Gaussian white noise waveform. I click it and put it on the block diagram. Here it is, and carry out the necessary connections. What I have done really here, I have just added the output. I have defined the amplitude, then the level of the noise here, the standard deviation. It could be the default value is, I think, 1. Maybe I have forgotten. I can take it away, and now look at this one, create constant. It is 1. So the default value, the standard deviation is 1, but I have connected 0.7, so I cancel this one, or I write here instead of it 0.07. Now it is this value. The other value I can cancel it. So I have defined the standard deviation of this signal. Maybe I can add the seed. The seed here is a value which is used to determine the repetition of generated signals for every run of the computer. Here it is the default -1. I keep it -1. And nothing more required. This is the output now. I connect the output with an AND, with an addition or add. Here, this is an add function. I right-click it, go to the visible items and label. Here it is the add function. So I am adding the generated noise with the pure sine wave, and I will get on the output a new waveform, which is noisy waveform. If I want to see it here, I right-click it here. I have already created an indicator here. So I right-click it. Here it is. This is the generated waveform with this level of noise, of standard deviation. If I increase from 0.7, for example, 0 0.5. Now the level of the noise will be higher. If I run the program, now it is another level of distortion. So I have just selected a moderate value, 0 dot maybe 1. It is also normal, and I run it. So this is the generated sine wave. Of course, it is a distorted wave with a standard deviation of the error equal to 0.1. So I have now created a sine wave with an added noise. Now I can generate a sine wave directly by using the simulate signal with a noise. I just right-click it as I told you. And now I shall here add noise. It is ticked. What kind of noise? I am adding uniform white noise. I did not add Gaussian, but I can add Gaussian white noise here. I can click it. Now I have a Gaussian white noise. If I want another type, of course, I have gamma noise, Bernoulli noise. Any type of common noises is available. Really, the white noise here is very common, the uniform white noise. So I keep it. It is added now internally. I press OK. And now here at the output, I get a sine with unified white noise. The output is taken here as this indicator. If I click it, this is the output with already generated sine wave with a noise. Now, after having both of these sine waves, I want to clean them somehow by using some kind of filters. Here I'm going to demonstrate for you how we can use Chebyshev filter and how we can use also Butterworth signal filter. This is the Butterworth filter. This is the Chebyshev filter. If you look at them, you can see that the high frequency side of the Chebyshev filter is very sharp compared with that of the Butterworth. And if you can see the band pass level here is leveled, it is practically constant for the Butterworth filter, but the signal at the output of the Chebyshev filter allows some level of ripple noise. Anyhow, we shall demonstrate both of them. So how to deal with this? I go again to the signal processing. Here we have digital filter. No, we have filters. And I select the type of filter I know. Here, filters. This is the Butterworth filter VI. And I think this is the Chebyshev filter, which I am also talking about. This is just, you want to click it and put it on the block diagram and then carry out the necessary connections. I have already done this thing for you. It is existing here. Now, in order for it to work, of course, you have to give at the input, to connect at the input side X, you have to connect the input, which is the sine wave with a noise. It is input here now. What else? What is this unit here? This is a dynamic data element which matches between the waveform which is generated when using the express VIs generally and for measurement in general. It automatically appears. If I take it away, let me disconnect it, for example, for you. the input is disconnected. And I now, sorry. I took it away. Now I want to connect the noisy signal to the input of the filter. Again, I am going to the input, and here it appeared again. As you see, it is, I can move it to see. So it is added automatically. If you want to know about it, you just right-click here and go to the Express VIs. Here, signal manipulation. At signal manipulation, you will see from dynamic data transformation to dynamic data transformation. So this, as I told you, created automatically. But if you want to know about them, you can right-click here. Sorry, what I have done, I should not do that. So I cancel it. Everything is in place. This is what I have. I right-click it here and go to the help. And at the help, you will find some information related to this LabVIEW element. Here it is, dynamic data type, convert from dynamic data to an array, which is I am doing now at the moment. But this is not necessary for me. Now I get out of it. I can cancel this one away. And so now I am here. The signal with noise is added to the input of the filter. What else? In order to get at the output the required filtered signal, I have to decide what is the lower and what is the upper frequency limits of the filter which I am going to work with. If I again right-click it and let me here show you it. So this is the filter, and as you see at the input, you have low cutoff frequency and high cutoff frequency, and the sampling also frequency. These are inputs to this VI, this function, and also the level of the ripple which you want is also having a terminal here, and also the order of the Chebyshev filter is also manageable. So you can make a lot of things to customize or to configure the Chebyshev filter. Anyhow, I don't need this Chebyshev filter. Now I get out of it. So what I have connected here, this is not my choice. This is the default values, but I can change them. So this value here represents, as you see, the low. It should give a reading that this is the high frequency, and this is the low. The lower one is the low frequency. Let me move it a little bit to be seen, because the pointer cannot touch it maybe. Okay. Now here, this is the low cutoff frequency connection. I am giving it the default value 0.125. This is the lower and this is the upper or the high cutoff frequency. And I did not add anything except also I have added the sampling frequency here. Here, this input, which is for the sampling frequency, this value is given as 1. It is not that high frequency. Okay. So as the output here now, I can get the waveform according to these settings. This waveform is shown as you see here. This is the waveform which I am getting at the output. If I run the program again for you, So you will compare now between this output and this is this distorted input, as you see, non-clean sine wave because of the added noise. This is a little bit cleaner and more realistic. Anyhow, as I told you, you can change it in any direction you want. I can, for example, instead of the 0.45, for example, take it 0.7 here. And now if I run the program, it will be with another more appropriate shape and closer to the sine wave. So this is the output, as you see. Now here it is not that sine wave, it is, as you see, going down, the maximum is attenuated exponentially downwards until it comes to a steady state value. It depends, of course, on the settings which you put here. This is not this Chebyshev filter. The output of Chebyshev filter, as you see, is here, as I showed you. But this is the output which is taken from Butterworth filter, because I have changed the level of the noise which is coming here. Anyhow, now let us look at the other case when for the generated wave with the noise internally, and this is the waveform which is at the input, and this is the waveform which is going to be at the output. So I am taking this now noisy signal to the input of Chebyshev filter. The lower frequency is given 0.01. The upper is kept as near as the default value. Here the .1 is the allowed ripple, this ripple here, which is existing at this portion here. It is very small value, but is allowed. I can also make it less, I can make it higher, it depends. Let us run the program now and see. This is the output. If I run it now, so this is the output now, clean as you see. If I change, let me try to change the ripple here and to increase it. Let us say it is allowable. It is allowable to have it 0.5, for example, instead of 0.1. Now, if we run, some ripple is, but it is not pronounced well. It is well filtered here. Let me make it 2, for example, and see what is there. It is also not that much. So it is working very fine. Yes. Now we have tested the Chebyshev file with both cases of the generated sine wave. Suppose we take the generated sine wave. This is the sine. This is the noise added to the sine. It comes here. Now we take this signal and input it to another type of filter, which is Butterworth filter. And I have taken the degree 2. Tier 2 is a second order degree, which is oscillatory anyhow. Let us keep it for now, and we can manage it a little bit later. And here again, this is the high cutoff frequency 0.7, and this is the lower cutoff frequency. The output should be this signal here. If I run it, here it is again. Let us manage the degree of the Butterworth filter and make it 1, because it could be 1 and 2 and 3 and maybe, and also a higher level, more accurate filters. So as you see now, with the first level, it is closer to the sine wave than the higher order one. Shall I try with a zero order? Zero order, I think, is nothing. It is okay because I am canceling everything. So I keep it 1. And we can, of course, I run it again. And let us manage the higher and lower limits of the frequency here. The sampling frequency is not, I didn't decide what it is. I can decide and give it a value. This is related to the frequency. Let us give it a value here. We create, for example, a constant. Here it is, the default is 1. Let me have it instead of 1, for example, 5. Now the frequency is 5. So it is improved a little. And let us, for example, change the lower cutoff frequency to become 0.05, for example. Now, what is going to happen? It is now a little bit better also, but I want really to manage it also by changing the upper cutoff frequency to become 2, for example, to see what is going to be there. And now if you run the program, it is now practically as a sine wave, except the low frequency side here, it is a little bit pronounced. This low frequency side could be managed also. Instead of 0.05, maybe if I put it 1, let us try. It is better. Okay, so there is no end for that. You can change it in the direction you want by variations of the frequency and the frequency limits and the ripple values. And the ripple values is generally for Chebyshev filters. Butterworth filter does not require that because it is leveled. It is leveled, as you see here. It has a good level. Okay, now what we can also see. Suppose we consider this virtual instrument or program here, which generates a noise, a Gaussian noise, but as you see, it is a waveform at the output. What do we mean by a waveform? When the signal is generated as a waveform, it is generated, as you see here, having 3 different components. One component, which is an array of the values, the real values of the signal. The other value, which defines the spacing between every 2 readings. And the third value, which represents the initial value at time equal to 0. So this is a time varying function with these, as you see, components. It is called in LabVIEW waveform. You can, of course, this cluster open again by using this piece of code, which is called here, as you see, get waveform components. Get waveform components. If you press it and put it on the diagram here, you will have it in this shape. You can expand it. And now you can connect the general signal, which is feeding it, as I did here. And you get at the output the components and have readings of it. For example, for our case, which we have here, the output, these are constants. dt is a constant value. So if you look at it, it is given 1,000 of a second, which means 1 millisecond. And the t0 is also given a value. What it is here, it is also a value. It is not, it is given a value, 0 value. The third, which is an array. This is an array of values. This is the array of values, which are the values of these components which are shown here. Now, if I want to know about this array, suppose I want to know the maximum value of this array. So I go to the array palette, and here is array maximum and minimum VI. I use this array here. I'll write it for you. Array maximum and minimum. And now here at the output, I connect at the input the same array, and I get at the output the maximum value. This value here, 0.35, is the maximum value here. If you look at these peaks here, you will find the highest one is this one here. Here is about 3. Here it is 4. Here it is going up between 3 and 4. Here is the maximum value. So the maximum component amplitude value is as shown here, which is 0.35. This is very useful for you. Of course, you can get other informations. For example, would you like to know the number of components there, the number of the elements which compose this array? These are the frequency components, the waves inside here. So, of course, I can also use the size array element. Let me give it for you. This is the size array, and feed the size array with the array itself of waves, and get the size here. The size will be about 1000. If I press it here, yes, it is here 1000. So I have here 1000 number of oscillations of sine waves, each of them, as you see, having a 1 millisecond duration. And the total, of course, will be 1000, as you see here, milliseconds. This information and management is very useful for you when you work with LabVIEW. Suppose I am working not with this VI. This VI, as I told you, is a waveform white noise waveform, but we can generate directly the output as an array. Here is uniform white noise, but this is an array directly, and there is no components describing the spacing between the elements in the array or the initial values. How to get it also, this is easy, I told you. Let me take away this one. Now, if I go to the signal processing and to the signal generation, here I find this is the Gaussian white noise, and this is the uniform white noise. This is not a waveform. This is just an array as the output. This is the function which I am using. If I write it here, it is exactly the same here, uniform white noise. Of course, I can get another one as Gaussian, no problem. I go again to the signal processing and to the signal generation, and here is the Gauss, and here is the Gaussian white noise, and make use of it. I have just put it here to show you that you also can generate this wave here. This is the output as a numbers here. These numbers represent the amplitude of instances of the array. The -1 here represents what is called the seed, which is used, as I told you, just to, because you are generating an array, and this array is generated randomly, so you need to keep the program produce the same values for every run. So you write it as it is default -1. This is the level amplitude of the output, and this is the number of frequencies 128. This is also the default value, but you can change it. You can write 189, for example. It is your choice. Here we have a waveform values, but we do not see the waveform here. If you want to see it, you need to go to the front panel, as you see here, to go to the graphs. You have waveform graph. Put the waveform graph. Now it is here. I put it here and connect this array with the graph. Now I can see at this graph a display of these values. This is a display of these instantaneous values which are here. And as you see, the magnitude as it is here 1, it is here 1, between -1 and between 1. Okay, what also I wanted to show you, I wanted to show you also how we can measure the frequency of a complex waveform or complex sine wave. I mean distorted with, which is composed of a number of periods. We use the tone measurements. Tone measurements is also an express VI. So if you right-click here and go to the to the express VI, you will find here something called signal analysis. And in signal analysis, you will find the tone measurements. Take it and put it on the block diagram. It is opened automatically as you do, as we have seen with the other express VIs, and you can also directly configure it in the way you like. Signal tone measurements. What do you want to measure? The amplitude? Okay, there is a tick. I want the frequency. I take the frequency. I want the phase. I take the phase for it. And you will have now here values, the amplitude and frequency and phase for the wave of interest. The wave of interest here is the wave. Okay. Now the wave of interest is the wave which I am feeding this VI. Here is the signal, really is the output of the Chebyshev filter. The signal after it is filtered, now it is fed to, I want to show you just, show you how. Yes, now. Okay, now I move this a little bit. I have place for it. Now I can move. Now it is seen. That's it. Now the signal at the output of Chebyshev filter is taken as input to the tone measurement. And I have configured it to measure for me what I want. The output here, as you see, the amplitude, the frequency, if I want. So the frequency here now, I have connected the output with an indicator here called frequency. If I click it to see where it is, here it is. So the frequency is, as you see, 0.05 hertz. This is the frequency. And this is the amplitude, which is about 1, 0.99, it is about 1. This is the output of Chebyshev filter. This is the output here. Here, look how the output is about 1. This is the average value is about 1, which is shown here. The frequency is also taken for the period. And what I have taken the amplitude and multiplied the amplitude by 2 to show you how I can manage the output. Then the output now is fed to the minimum maximum function, and I get here the minimum and maximum values. The minimum value 2999, this is the maximum value, and the minimum value is they are the same. One of them is the minus side and the other one is the plus side of the wave. This is just to show you that instead of having here at the output, when I multiplied it by, here it is not really 1 only, it is multiplied by here's the real amplitude. It is about 0.999. This is the amplitude, and it is multiplied by 2. I will have the real output. Okay, so this now is not necessary. It's just to show you what it is. So let us make a summary. What do we have and what I have shown to you? Let me show you it from here. Okay, Windows. Okay, so what do we have here now? We have generated a sine wave by using the express VI here, and also we have generated another wave of the same type. But this wave was generated as a clean one, and this one was generated with a given level of noise internally. The output signal here is added to a noise generated by this Gaussian white noise waveform. And now we have here a waveform which is with a noise component. And this waveform now is fed to Chebyshev filter. It is filtered and shown there at the front panel. Here it is. Now, if the other thing which we have done, we have generated the noised sine wave, and we have directly fed it to Chebyshev filter, and the output also, which is already cleaned, is shown here. Look how the difference between this one and this one. Now, one more thing, I have shown you how we can use Butterworth filter as a first order or as a second order, and a little bit the difference between the performance of the Chebyshev filter and the Butterworth filter, and we have got the output to different waves, but either of them is now clean comparatively with the input. The last thing which we have done, we have used the tone measurements to measure the amplitude or the frequency of a complex compound signal to get an idea about the average value. Also, I had explained to you how we can generate waves, noises, or other signals, either by using directly waveform or by using an array structure. When we want to know the components of the waveform generated signal, here this element which is used, get waveform components, gives you the chance to see what is the time space between every component and the other component, the near component, the neighboring component. It gives you an information about the value of time at the beginning, and also it gives you an array of the values of the generated signal. Well, I hope that this is a very simple and introductory tutorial, will help you how you can manage waveforms and how you generate different kinds of standard signals, how you can filter them, and how you can carry out some related measurements. Thank you very much. Wishing you the best.